Rubin is like difficult to make an introduction because he's known for so many things, like what? Bayesian bootstrap, causal inference, multiple imputation, missing data. In fact, I learned from him like many years ago that the causal inference is a problem of missing data. Okay? Because if I have to tell you all the achievements that I don't have over the years, it will take me the whole hour.
Oh, yeah.
And I'm going to allow them to tell you his achievements over the next hour. Again, a great pleasure to have you now, and please join me in welcoming
Well, thanks so much for inviting me. It's a pleasure to be here. We have many friends in common, and so maybe I'll even see some out there. One or two. Okay, so this talk is my take on causal inference and how it's developed over the centuries. And it's sort of an idiosyncratic. I mean, Alberto sort of indicated that we all have sort of idiosyncratic views of work that we've done and the field that we're in. And what I mean by remarkable history is I do find it remarkable in that how recent we, I think, statisticians, economists, have come upon a pretty correct or deep understanding of causal inference. And so because it is an idiosyncratic view, I sort of start out by giving you sort of my history and how I got here, got into these views. So it's sort of a prologue to causal inference. And my introduction to actually statistics, causal inference, and other things was actually started in high school. Like many of you guys here, when you're in high school, a lot of people are drawn to math and physics. I was more drawn to physics than I was to math. And I think one reason why a lot of us do that is it's an easy thing to grade. When you're grading, you get the right answer, you get the wrong answer. If you're thinking about art, who's a good artist? I don't know. There's a lot of subjectivity. It's not that easy to grade. So when I was in high school, I started to take physics, and I loved this stuff. And in it was the very early days. I graduated high school in 1961. And they just give a hint in this physics, high school physics, about relativity and quantum mechanics, which is just the hint of it. Certainly not saying I understood it back then. But then when I went to college, I entered Princeton in 1961. And the physics course I took was from this great guy, John Wheeler. And Wheeler, I don't know, everybody heard of his name? Yeah, he's a well-known physicist. I guess he's best known for a couple things. One is he's credited with having made the name black holes, which he denied. He said he was giving a lecture, and he was describing what was now known as a black hole. So dense that even photons can't escape. And somebody in the audience said, "It's a black hole." And he tried to find the guy afterwards so he could attribute it correctly, but he never found him. So if you look in these sources of all information like Wikipedia, he's given the credit for having invented that name, but he claims he didn't. Another thing that Wheeler is noted for is being Feynman's PhD advisor. So he was a great Wheeler was a great teacher in some ways. For example, one lesson he said, this is 1961, said, just because you read it in a scholarly book, don't believe it necessarily. And he had an example. At that time, the textbook that we had was this great fat yellow thing, Halliday and Resnick, maybe it's even still used now. And there was he pointed something out. There was in one of the chapters on electromagnetism and vectors, there was a talkie proof, not a real proof, but a sort of talkie proof that you can't have coherent light. And I think the Halliday and Resnick that we had was a 1959 or 58 edition. What's coherent light? You obviously know. Yeah, a laser. And so, you know, everybody now has lasers, but here was a talkie proof you can't do it. It's basically, just because it's you read it somewhere doesn't mean it's true. He also was very big on being able to approximate things with logical reasons. And I remember the first homework problem that we had was, how far can a wild goose fly? And I don't want the exact answer, but I want you to describe what you have to do to figure it out. Well, you know, so how can a wild goose stay up in the air? You know, gravity's pulling him down. There's potential energy and there's kinetic energy. He's burning fat. That's how he stays up in the air. Well, how much does a wild goose weigh? Can it weigh a ton? No, come on. And how far can it fly? So give me the steps that you're supposed to go through to get an answer to that makes sense based on your understanding of physics. And so that was useful. And also, you know, in relativity, he would describe it in terms of, see, remember this problem. There's a guy carrying a 20-foot pole. So he's a pole vault. So he's running horizontally, and he's facing a 3-foot outhouse with a door on each side of it. And you see him running, one door opens, he runs inside, the door closes, and later the other door opens and he runs out. And that's what you see. So how can you see that? All you guys should know, be able to do that, right? What has to happen? Obviously, he has to be running very, very quickly, right? And you have to be far away. And what makes it possible? Light has a finite speed, right? So you see one thing, and if you're far enough away, that's what you'll see. One door opens, he runs in, the other door opens, and he runs out. And so you should be able to explain that, you know, not in terms of equations. I mean, he was good that way too. You know, you don't write down silly equations, but you understand what the equations are trying to say. There was another guy who was influential at Princeton, and this guy was completely different in some ways. His name was Julian Jaynes, and I met him in 1964, I think. He was a psychologist who was writing. He hadn't written a book then, but he wrote a book in the 70s, and we used to go drinking all the time and talk about this stuff. And basically the book was, what was the name of the book? The Origin of Consciousness in the Breakdown of the Bicameral Mind. And the idea here is that if you look at the Old Testament, most of it was written by what he would claim were unconscious people. If you look at the Odyssey, it was written by unconscious people. So what do you mean by conscious and unconscious people? Well, he basically said that unconscious people heard voices from one hemisphere to the other hemisphere and interpreted these voices as voices from gods. And the gods were solving problems. And if you listen to or read the Old Testament, the stories, you know, God came to me last night, sat down in bed, woke me up, and told me this. New Testament is almost all conscious people. I had a dream last night. In my dream, God came to me. So these unconscious people communicated between the two hemispheres by hearing voices. That's why this related to what we were talking about earlier, about people having different reactions on the dominant and subdominant side. And at some point in time, these people existed side by side, and eventually the people who were conscious became dominant. And why did they become dominant? Well, this ability to realize it's an internal conversation allows you to deceive. And deception became an important part of survival. So kids, when they're under 2 or 3, are sort of pre-conscious in the same sense. They'll lie, you know, sort of like Trump. They'll just lie, they don't care. They'll say stuff. And then you should believe it. Why? Because I believe me. You know, what do I know? So, but at some point, we sort of had this, we human beings evolved to where we heard this as internal conversation between having a conversation with yourself rather than having a conversation with a God. So if you look at why are there multiple gods? God of war, God of Cupid, and all this other stuff. Yeah, that's what I'm telling you. Yeah, she's cute. Go get her. Fight the battle. Trojan horse. It's a completely ridiculous story. We've been sieging you for months, and we're now going to make a gift. Oh, okay. Oh, nice. Thank you so much. We'll take the gift. So the reason why that's impressive is that everything we think we know or do know is filtered through our brains. There's no doubt about that, right? That's how you think. And the idea that this internal conversation is always taking place was also very influential to me. As an undergraduate, I studied various kinds of things, and when I was in graduate school here, I was in 3 different departments. And eventually I got into statistics, and primarily through this guy, William Cochrane, who was this great Scottish statistician. And one of the early courses I took from him was experimental design, classical experimental design. Randomized blocks, Latin squares, partially balanced and complete, fractional replication, all that good stuff. But the thing that was impressive about that is in that course, the idea of what causes what, you learn through experimentation. And that was completely consistent with what I brought up in high school to think about physics. If you want to learn about something, what causes what, ideally you should intervene and change something and see what happens. Or you should have a theory. Hypothetical interventions are okay. But you should be able to describe what kind of intervention it is that you're contemplating. And cause and effect is tied to the idea of interventions. That you did the intervention, hey Josh, or don't have the intervention. And in these discussions in physics forever, or with Cochrane in experimental design, there's a clear separation between the science, which is the object of inference, and what you do to learn about the science. That's what sort of man does to learn about science. He intervenes, or he thinks about intervening. But there's a clear separation between the science, which is the state of the world now, and what you do to learn about it, which would be something you'll do tomorrow, and how you infer, which is something else. And so science exists, the universe exists, and the way it exists right now can't be affected by something you do later. So time marches on. That was another sort of lesson that I sort of. I'm not saying any of these things are absolutely true, or that my understanding of them was perfect. I'm just saying this is where my idiosyncrasies come from, and where I think about stuff. And so you have the same notation, representation of science, no matter how we try to learn about it or measure it. So science exists, then we do something to intervene to learn about it, and then we build models. But the science exists, and the same notation is used to represent that science no matter how we try to learn about it. So there's this big separation between science, the object of inference, and what we do to learn about it. Part of that was missing data always exist. So that's what Alberto said, yeah, causal inference is a missing data problem. Because you can't go back in time. You can't go back in time and undo what you did. What was it? What's done cannot be undone? Where's that from? Was that a great scientist who said that? Come on, guy. Who's famous line from a play? Shakespeare? Macbeth? What's done can't be undone. You can't go back in time. If you have a headache and you take an aspirin to make your headache go away, you say, well, what would have happened if I didn't take the aspirin? You can't go back and get rid of the aspirin. You can't go back in time. And this idea that you can have scientific estimands, things you want to estimate, that you can't measure precisely, was natural to me. Because even in high school, I said earlier, that I got a little touch of quantum mechanics. Heisenberg uncertainty principle. Can you measure position and momentum at the same point in time? No. Do they both exist at a point in time like 2 seconds ago? Yeah, they both exist for any particle. It has position, it has momentum. Can you measure both? No. Precisely? No, you can't. And that's sometimes confused with this thing called the observer effect, which is different from this quantum mechanics, the Heisenberg uncertainty principle. But observer effect is to observe something, you have to bombard it with photons or electrons or something. And that the act of measuring actually distorts the position or distorts the momentum. And that's just a fact of life. So you cannot go back in time. The missing data always exists, being able to but it doesn't mean that the scientific quantity doesn't exist, or the scientific quantities don't exist. They both do. But you can't measure them both. So I just grew up believing that. Now, if someone's going to tell me it's not true, I don't know, but I'm saying that's why I have the idiosyncratic views I do. About causal inference, that's why it's a missing data problem. Sure, it's sort of obvious in some sense. But what is these essential ideas? Well, I think in some sense, Ronald Fisher was one of the first essential ideas. And in 1925, in the first edition of Statistical Methods for Research Workers, the last chapter is on randomized experiments. Some people attribute Fisher and randomized experiments to Fisher 1935 with design of experiments, but that's wrong. People often are kind of sloppy. If you read the preface to Design of Experiments, what did he say? Well, basically he said, this last chapter in Statistical Methods for Research Workers, which has gone through various editions now, and it's become clear that the design of experiments, causal inference, he didn't call it causal inference, I don't think, but anyway, the design of experiments is a too important a field, a topic, to be buried in the last chapter of a book. So I decided to write a book about it. It's not literally what he said, but it's basically it. And therefore, having written a book about it, I can get rid of the chapter in Statistical Methods for Research Workers. So people who attribute randomization to 1935 have never read the first edition of something. They just say, well, it wasn't in Statistical Methods for Research Workers, and I've read the 1962 edition. Well, that's not the same as the first edition, 1925. So Fisher basically proposed actually doing randomization. Now, it turns out there are other people who talked about if you had randomized. So Gossett, student, has stuff written in the 20s. If you had randomly assigned the plots to that, then the expectations would be mumble, mumble, mumble. So there are other people doing mathematics who showed if you had randomized something, you would get these expectations right, in the analysis of variance kind of stuff. But Fisher was the first to actually propose you should actually do it. And thereby, some of the talky things are what makes randomization good. Well, thereby you create balance on all pre-treatment variables and expectation. People well before 1925 understood expectations, but nobody actually talked about this kind of randomization. So recondite advice from Fisher, which is not really written in anything that's easily found, is to actually re-randomize if you got a bad allocation, just randomly choosing it. If you got an allocation where all the treated people were male and all the control people were female, for example, what should you do? Fisher never wrote this because but what he said was you should re-randomize. Don't live with a bad randomization. Josh, you believe that, don't you? You should not live with a bad randomization? Right, and that's what did Fisher, because if you recommend doing something that you do, but you want people to do randomization, it's kind of awkward to talk about the problems with randomization, so just don't mention it. But I know you re-randomize. But and the reason why you don't talk about it is because none of the relevant test statistics are really correct. So the F tests are wrong, even asymptotically. The T tests are wrong, even asymptotically. All the usual stuff is wrong because you're getting rid of the tails of the distribution, which makes symmetry arguments work. So if you throw away the tails, it's no longer symmetric in the same way. And that's why it was recondite advice, because I talked to Cochrane about that. He said, and one thing that's interesting is the theory and application of this re-randomization is finally being pursued. I'm pursuing it with some articles are with a former PhD student of mine who's now at Penn State, Carrie Locke Morgan. And there's one paper in the Annals of Statistics and another paper in Journal of the American Statistical Association. And it's beautiful theory, actually. And and the asymptotic distributions turn out to be truncated distributions. They're mixtures of truncated normals. They're no longer normal. And again, it's sort of beautiful theory because all the geometry still works. But the problem with the results are that they're worthless for inference without computers. You can't tabulate the things. They're too complicated. But you can, if you have a watch or a telephone, you can do it. So, but guys back then didn't have these fancy watches that we have now. So why pursue something that you can't do, that you can't really recommend to anybody because it's wrong? Another great contribution of Fisher's was this randomization test. A null hypothesis says there's nothing going on. The treatment is exactly the same effect as the control. Therefore, under that null hypothesis, when you've done one randomized allocation and see the outcomes, you know what you would have seen under all possible randomizations. Right? I know everything. So if the aspirin has no effect, then I know what would have happened if you hadn't taken the aspirin. And I can do this, get the full randomization distribution under the null hypothesis. Now, is that a new idea really due to Fisher? Well, in some sense, no, because he was working at Rothamsted Agricultural Station, and they've been doing what they called uniformity trials for hundreds of years. Take a bunch of plots of land, and you apply the same fertilizer or the old stuff, whatever it is, and you measure and plot histograms of the yields from these different plots, and you get histograms. Let's suppose you have 100 plots, and you have the yields across these 100 plots. And then you apply a new fertilizer, and you look at the average yield under the new fertilizer, and you locate the new fertilizer in the histogram of the old fertilizers. And if it's out beyond and if you have 100 plots from before, and this new fertilizer works on this plot, and it's better than all 100, what would you be likely to say? The new fertilizer appears to be significantly better than the old one. And if it's out in the tail, like 1 out of 100, his percentile value is 1 out of 100. His p-value is 1 out of 100. Completely intuitive. But the idea, but Fisher's idea is that under the null hypothesis, you know this distribution. You don't have to make assumptions of exchangeability in time or exchangeability in weather or other stuff. You know, under the null, you know the null distribution. I mean, it's completely intuitive. I mean, we make use of this idea all the time. For example, you go to 100 restaurants and you have a mental histogram of their quality, and you go to a new restaurant you haven't tried before, and it's better than all the other ones. You might say, hey, it's significantly better. And what's the percentile value? If you had it's 1 out of 100. Completely intuitive, except Fisher had this blast of insight that under the null, and he was a mathematician, he was a good mathematician, very good, that under this null hypothesis, you can get this distribution without all these extraneous exchangeability assumptions. Stochastic proof by contradiction of a sharp null hypothesis. And I view this as a special case of something that's completely Bayesian called posterior predictive p-values that actually defined this in an Annals of Statistics paper in 1984. And I think that it's having some action these days, some attention, because again, it's one of these things you couldn't compute. Because you're basically running Markov chain Monte Carlo kind of algorithms through stuff in order to get answers. But it's somewhat surprising, however, that he never had any real notation except under the null hypothesis. He never had notation for what causal effects are except under the null. He clearly knew what he was doing, though, because here's a quote from 1918 from Fisher. If we say this boy has grown tall because he has been well fed, we are not merely tracing out the cause and effect in the individual instance. We are suggesting that he might quite probably, kind of awkward English, might quite probably have been worse fed, and in that case he would have been shorter. So we got his height being well fed, and we got his height being poorly fed, and the causal effect of his being poorly fed versus well fed is the comparison of these two things. One thing you can see, one thing you can't see. But he had no explicit notation for formalizing these non-null causal effects, despite this tremendous geometric insights under the sharp null hypothesis based on symmetry arguments. In fact, he never wrote down any algebra for these F-tests. He just derived the distributions, all based on symmetry arguments. And in fact, according to Cochrane, he ran into a lot of trouble later in his life when these mathematical statisticians were doing all the algebra like Wilkes, to derive these distributions. And he said, what are you doing? I've already proven that. You just think, use the geometry, it's obvious. Symmetry and normality, I mean, it's obvious. So why go through all these tedious proofs? It's just, tedious second grade mathematics. Who made up the notation then, using potential outcomes? Where there's one outcome if you got treatment A, and another outcome if you got treatment B. That was Jerzy Neyman of Neyman Pearson fame. He wrote a master's thesis in 1923 in Poland, and it was written in Polish, and he described an experiment. It's like old mathematics. It's horribly written. Where you have an urn, and each plot had an urn, and you're picking balls from the urn, and the colors of the balls would tell you which fertilizer to apply, bizarre stuff. And if you chose a red ball here, then you had to take a red ball out of all the other urns. But mathematically, what he was describing was a completely randomized experiment. Didn't describe it that way, but it was. And he defined the estimands in randomized experiments as functions of these potential outcomes for the n units. Now, if n plots of land, y0 is this column vector of n components, which are the array of potential outcomes under the control treatment. y1 is an n component vector of the array of potential outcomes under treatment 1, etc., and implicitly assuming something that I call stable unit treatment value assumption, which is really just saying that the outcome for outcome is y. The outcome for plot I being exposed to treatment W is a function of I and W. That's all that it means. So it can't be something undefined. It can't be something that depends upon something I'm not telling you about. It's a function. But you can't observe both in any one unit. And Neyman in 1923 was explicit about that. You can't observe both in any one unit. And somehow it didn't really bother him back then. There were features that did bother him, but somehow, even though he didn't talk to the Copenhagen School of physicists who were doing quantum mechanics, It's the same as Heisenberg. You can define something, you can define the causal effect on this, based on this comparison, but you can't measure it. A second great contribution of Damon, in addition to this notation, which he poo-pooed later in his life, he evaluated the operating characteristics of procedures like estimators or interval estimates over the randomization distribution. So just like Fisher, he had this idea of the randomization distribution, all possible randomizations that you could do. But he evaluated the operating characteristics. So this evaluation turned into Neyman Pearson. So all of Neyman Pearson was sort of founded on this idea. And basically, my view of Neyman Pearson is just, it's showing that it doesn't, the whole series of technical arguments is really a series of things showing that it can't work in general, because it's too limited. One thing he worried about in 1923 was the role of non-additive unit-level causal effects. So the causal effects are additive is if for each unit, for each plot, the difference between its yield under the new fertilizer and the old fertilizer is constant. It's a constant effect. You can't ever observe it, but that's the definition of it. And if it is additive, then the correlation between y1, this vector y0 and y1, correlation between those two vectors will be 1. And he worried about it back then because what he was after was to get an interval estimate for the average causal effect, the average of all the y1s minus the average of all the y0s. What's now known as the confidence interval. So they knew about asymptotic normality, so he's willing to assume asymptotic normality, but he wanted to get an unbiased estimate not only of the average difference between y1 and y0 across the n units, but he wanted to get an unbiased estimate of the sampling variability of it. He said, but that unbiased estimate depends upon something you can't estimate, the correlation. Turns out later in his biography, written by Nancy Reed, I think, he denied a lack of understanding. But he said, I was just fooling around with stuff. I didn't really know what I was doing back then. I was fooling around with algebra. I didn't understand the depth of it. And in fact, even though I described a completely randomized experiment, I had no idea, at that time, I had no idea that I should advocate it. So that's Fisher's idea, not mine. This is after they hated each other. He still said that. It's due to Fisher, not me. All econometricians are that generous, aren't they, Josh? Right. We're too. A nasty one, it seems. So comments on these insights. To me, these are 20th century insights, like those in quantum mechanics. The estimands, quantities to estimate, the scientific quantities to estimate, are defined in terms of measurable quantities, which are not simultaneously measurable, like momentum and position. Causal outcome, potential outcome under treatment, potential outcome under control. So they're not even theoretically measurable. It's kind of odd. It's almost like if you believe at all in psychology, there's this Jungian collective unconscious. So the Copenhagen guys were talking about quantum mechanics, and here's Neyman who had no idea about the Copenhagen School of Physics. These same ideas. You're finding something in terms of something you want to estimate, but it's in terms of unmeasurable quantities. So I can't find any link beyond that. One question that often arises, was Fisher really the first to propose actually randomizing? There's a guy named Perce, who was a psychologist, philosopher in the late 19th century. His father was, I guess, a famous Harvard mathematician. But Perce proposed, I've had these conversations with Steve Stigler, who's our historian in statistics. In fact, I just saw him last week. And he believes that Perce did say something about it. Perce may have anticipated Neyman in survey sampling, but I don't think he anticipated Fisher, because he was doing psychophysical experiments where you're picking objects up, and you were blindfolded, and did this, the second object feel heavier or lighter after picking up a heavier or lighter earlier object. And he randomized the order of the objects. Did Perce have anything to do with inference, like the randomization distribution, the null hypothesis? No. So did he understand the purpose of the randomization was so the guy couldn't anticipate the psychophysical, the guy in the psychophysical experiment? Yeah, that he did, but it had nothing to do with inference. So I think that Fisher probably was the first. I'd be curious to find out if there were other references that are more recent. But after Fisher design of experiments in 1935, it really became clear that these randomized controlled trials, we actually did randomization, quickly became to dominate agricultural and animal breeding. Because the people who did real experiments, not necessarily randomized experiments, but bred falcons or bred cows or bred horses, thoroughbreds, that goes back for centuries, thousands of years. And those guys kind of understood cause and effect. Then they said, well, why am I breeding two thoroughbreds together, two fast racing horses? Because I'm going to get a better offspring. They'll be a better runner. So people who actually did experiments, they sort of understood it. Philosophers, they're totally confused. So, John Stuart Mill is often credited with stuff. He had this constant conjunction. Every time I do this, every time I open my hand, the bottle falls. Therefore, my opening the hand causes the bottle to fall. It has to happen every time. Who used this as a defense in the 1960s? Well, if this is John Stuart Mill, I mean, he's a great man, right? So does cigarette smoking cause cancer? According to Mill, it has to happen every time. Does anyone know a cigarette smoker who didn't die of lung cancer? Yeah. So therefore, cigarettes cannot cause lung cancer, according to John Stuart Mill. Was that a useful definition? No. In fact, even subsequent philosophers aren't very helpful. But randomized trials quickly dominated agriculture, where people were doing experiments anyway, and they sort of they knew the score. Agronomists knew that you put good fertilizer on it, it works well. Animal breeding throughout the Commonwealth, because in India, Australia, they understood this stuff. And more applied work was done in the United States. Texts by Kempthorne, Oscar Kempthorne, a Welsh guy, Cochrane and Cox, Gertrude Cox, George Box of Wisconsin, David Cox, different Cox, David Cox in England. All did, they wrote great textbooks on this stuff. They may be outmoded now, I think they are, because of the computer revolution and this ability to re-randomize. But they understood. Supporting mathematical work was, a lot of it was done in India at the Indian Statistics Institute, where Mahalanobis founded that place. And then the guys there were R.C. Bowes, Nair, C.R. Rao, who's still alive at 96 or 97. And subsequently, after sort of taking over animal breeding and agriculture and agronomy, they subsequently entered these randomized controlled trials, entered Western industry after World War II. They actually were used to make parts for automobiles, how you manufacture stuff. And after World War II, they actually entered Japan after we destroyed the country and destroyed any industry that they had. There was a guy named Ed Deming, who was a consultant, lived in New York. And we sent him to Japan, and he introduced randomized controlled trials and quality control in Japan. And every year, Japan gives a medal called the Deming Medal in experimental design quality control for this guy, Edward Deming. So it completely ended. If you go back to the 50s, anything that said made in Japan was just complete crap. And then they started doing real experiments in quality control. And you get by a Honda in the 60s, runs forever. So they took it seriously. But an interesting thing is these insights about randomized controlled trials were limited to randomized controls with non-conscious units. This sort of gets back to some extent to the Julian Jaynes comment, thesis about non-conscious. I mean, actually, somebody once mentioned to me that actually rats do have personalities and they can be affected because they're raised in litters and you randomly choose from the litter and move them to another place, and they don't like that. So they're affected by placebos. So the transportation of these insights of randomized to randomized controlled trials with conscious units was very, very slow. As far as I can figure out, this could be wrong, the first ones in medicine, dealing with people, medical treatments for people, were in the UK in the 46, the Medical Research Council in Sir Bradford Hill, and streptococcus. Antibiotics for streptococcus, I think. In the US, there's a Salk vaccine trial that was started in the US in 1954. The US and FDA, what was done before the 1950s? How were drugs approved in the US? Did they do randomized trials? No? Nothing. Get a bunch of docs together and let them make recommendations. And they were paid by pharmas to make recommendations. That's how drugs were approved. This guy, Paul Meyer, who was at that time was at University of Chicago and since moved to Columbia and died recently. He was a big pusher for the use of randomized trials in the US. And I think, in fact, if we go more recently, that this overzealous adherence to intention to treat principle. Intention to treat principle says you should analyze the data as they got randomized, not analyze the data by how you got treated. So if I randomize you to take a pill, you don't take it, you flush it down the toilet, I'm going to analyze the data as if you took the pill. And Sir Richard Peto is a big advocate of that. And I think it's a mistake because, in fact, if you look at FDA, most of the drugs that are approved, their dose level is based on the randomized trials, where some of the people are non-compliers. Some of the people throw the pills away. And in time, the dose levels are ratcheted down. They say the dose levels is approved are too high. What's an example, a dramatic example of that? Probably you know about it. Maybe not. Maybe 20% of people here probably taking the drug. The first ones were approved about 1950-something. And the dose levels are now as low as 1/10 of what they originally were when approved.
Birth control?
Yeah. Where they find all sorts of cancers. You know, you do a randomized trial, and you want the dose to be relatively high, so the drug will be approved. It works. So you have a relatively high dose, and as originally, in the original trials, they were high enough that women could skip a day or two and still be protected. But then you find out later that if it takes it for 5-10 years, cancers. Cancer is more prevalent. So the dose levels have been ratcheted down in time, as low as 1/10 what they originally were. I think in the U.S. it was, but I think that this streptococcus antibiotic was done in the U.K. earlier, a couple of years earlier. Maybe 5 years earlier, actually. Because I don't think so. At least when I tried to look it up, I didn't see anything about that. It's an interesting point. Yeah, I think that's right. Well, certainly with Salk vaccine, it was with kids. I don't know about the UK study because I think it was. But strep. I mean, there are a lot of diseases that if you're an adult, in those days, you've already been exposed naturally to the stuff, so you have natural vaccination to some extent. So these drugs, as originally approved for these diseases that could be fatal if you're a kid, I think were primarily done in kids. But surprisingly, there was no use of these Fisher-Neyman insights or the notation in non-randomized trials. And so here we have these insights in the context of randomized trials. And then when they go to dealing with observational non-randomized data, they just ignore everything. What I mean by they, well, a dramatic example of that was the 1964 US Surgeon General's report on cigarette smoking and lung cancer. The statistician on that committee was Bill Cochran. And that's how he got interested in, when I was a graduate student, why he was interested in observational studies. He's always would teach about randomized experiments and classical experimental design. That was one of the things he did. But if you look at the Surgeon General's report back then, what did they do? Regression. Logistic regression, least squares regression, just regression. Looking at regression coefficients as if they're causal effects. No use of this fantastic idea, due to Neyman, I think, of the comparison of potential outcomes defining causal effects. And causal inference being a missing data problem. No insight at all.
Why?
I don't know why. I mean, when I look back, it's I just say, well, you know, Cochran was, when I took this course from him, he also taught a course in '68 on observational studies. And he just leapt right into regression. Everybody was doing it that way. The epidemiologists, economists, social science, psychologists, they all just did regression.
Sorry, but Fred Mosteller was around too. So why did they do experiment? Why wasn't this part of the report? I'm just curious.
You have to ask them, I think. Because, I mean, do I know why? No, I can't understand why not. I mean, because I talk to Cochran all the time about this stuff. And this is just the way it's done. You can read, I think, his 1965 paper in JRSSB, Journal of the Royal Statistical Society, Series B. He talks about the analysis of observational studies, or some title like that. And he's Sir Bradford Hill and the criteria for causality. Nothing about the insights from experimental design. But the only thing he says there that gives a hint of something is he said it's often worthwhile asking. Was Hill's advice? Someone else. That if you could do a randomized experiment, how would you do it? And that's the only thing that in this article by Cochran that indicates that there's something there to learn from thinking about it as if you could do a randomized experiment. Maybe there's some insight there. But again, they didn't do it. Economists didn't do it. It's always regression. And the causal effects then became parameters in a model. They weren't something that you could actually see. You know, parameters don't exist. They're completely hypothetical. We just make them up all the time. But the things that exist are values that you could observe. Even if you can't observe causal effects, they're defined in terms of things we can observe. And that seems to be this insight that for some reason never made its way across the randomized trial barrier into brains of people looking at observational data. I don't know why. Because again, I grew up with it, so it seemed obvious to me.
It's like a bicameral mind.
Yeah, that's right. That's right. You're waiting for the gods to tell you to do it, in some sense. Why they didn't do it, I don't know. In fact, that's where this thing, Rubin's Causal Model, RCM, it's for a series of papers that I wrote. Actually, I wrote them in the late 60s, but I couldn't get them published. Because basically everyone was saying they were wrong. So this paper in '74 actually ended up in a journal of, what is it, Educational Psychology. Why there? It's the only place I could get it published. I knew the editor, so he was willing to publish it even though it was crazy. Now it's got 8,000 references or citations or something like that. So it seemed obvious. So I wrote this sequence of papers, and they eventually became, quote, more and more respectable. The '78 paper was in the Annals of Statistics. And what were the contributions of this? Well, again, it seems sort of obvious to me, so in hindsight, I guess there were some contributions, but one of the potential outcomes defined causal estimates in all situations, not just randomized experiments. So the science is defined by the potential outcomes. And it's not just in randomized. You don't have to say exactly how you can do the randomized experiment. You set up the potential outcomes. And if you try to learn about it through randomized experiments or observational studies, the notation, the science remains the same. Actually, in the mid-'70s, I had a sabbatical year off, and I spent it at Berkeley, where Neyman was still. And there was Evans Hall. And the top floor of Evans Hall is where the retired faculty had offices along with the visiting faculty. And I had an office next to Neyman's. And we used to go out to lunch together and talk about this stuff. And he disagreed. He said, without randomization, talking about cause and effect is too speculative. Let's talk about the stars. Because he was into astronomy then. And they had a big telescope and sitting up there in Palomar. Chain smoker, too. I mean, during lectures, he would literally, this one got low, take out another cigarette and light it from the cigarette that was going out. Of course, all faculty meetings were smoke-filled back then. So he disagreed. It's too speculative, and who was going to argue with Neyman? So I just went on and did my thing. Because this is very consistent with what he said about Fisher. Fisher made up the idea that you have to do randomization to learn about cause and effect. Another contribution is you needed an assignment mechanism for causal inference. So you needed to set up the science, and the assignment mechanism was the probability for the treatment indicator given the science. It's the mechanism that creates missing and observed data. If you have missing data, you have to say something about why it's missing. You can't just fill in the mean or some other stupid thing. So therefore, you have the science, and then you do something to learn about the science. You intervene, and you assign some units to some treatments. Other units get the other treatment. Seemed obvious to me. But apparently, no one ever wrote it down before. It's just it's a particular missing data mechanism for creating missing data. Probability for treatment indicator W given the science. So in general, the indicator W, this treatment indicator 1 or 0, given covariates X and potential outcomes, generally depends upon the potential outcomes. And the idea that some assignment mechanisms are like that, I mean, there's a lot of babble about that, but there was never any notation for it for some strange reason. So Roy's model in the 1950s, right, the economist, talks about self-maximizing behavior. You want to choose things that maximize your wealth or your life or something like that. But no notation at all, no math anywhere, just the statement. Well, that's not sort of a blast of insight, but I mean, there's discussion of it before. And then an unconfounded assignment mechanism is one where the probability distribution doesn't depend upon things that are missing. So it doesn't depend upon the potential outcomes. It just depends upon observed covariates, blocking factors, age, sex, education, things like that in the past. That's what a randomized trial does. It makes the assignment mechanism unconfounded. So it doesn't, and this is just standard of applying this to an assignment mechanism wasn't done, but the word unconfounded is a long history in experimental design, where it's talking about factors in an experiment being unconfounded or not aliased with each other. And there's another extension which is relevant for Bayesian inference, which is ignorable, like in a sequential trial where you're playing the winner. You want to assign the treatment that looks best now, so first one gets randomly assigned, the next one gets higher probability for the treatment that looks better at that point in time. But that's all basically frequentist inference based on the randomization distribution. And what does Bayesian do? Models the science. Put a model on these covariates and potential outcomes, in addition to the assignment mechanism, which creates missing and observed potential outcomes. And what I say an artistic touch is needed here, well, that's because all models are wrong. These are just approximations. So least squares is just a linear approximation. It's wrong too. You know, George Box is often credited with this great quote, all models are wrong, some are useful. But, well, John von Neumann said that before as well. Right? He said, you know, but the real world is much too complex to be fit by any simple mathematical model. It's life. So, an artistic touch is needed because you don't believe the model, really. But it's highly useful just to address all kinds of problems. The fundamental problem facing causal inference is a phrase I made up in 1975. It is a missing data problem. For each unit, even under this stability assumption, you can only observe yi1 or yi0. The other ones are missing. And therefore, you need a model on why some are missing and some are observed. That's this assignment mechanism. And the random, for example, the random assignment of active versus control implies a representative sample of the y1 values will be compared to a representative sample of the y0 values. Totally obvious in some sense. Well, if it's totally obvious, why didn't the Egyptians write it down? Well, I mean, they got the circumference of the Earth within what, 100 miles or something like that, by measuring the shadows from pyramids. So they're not stupid. So why did it take thousands and thousands and thousands of years to have this insight? Well, two things. You have to have this notation as a missing data problem. And then you have to realize that if I randomize y1 or y0, I have a representative sample of y1 and a representative sample of y0. But you have to have a model on the assignment mechanism in order to draw inferences about the missing potential outcomes. And it's a mistake, bad mistake, to regress the observed value of the observed value of the outcome for unit I on wi. That's what everybody does. It's least squares. You lose the potential outcomes in the key Fisher name and concepts when using this observed value notation. The observed value notation mixes up the assignment mechanism of the science. Which is it? Is it a scientific quantity, or is it something we did to learn about the science? It's got both of them in there. It's got the science, and it's got what we did to learn about the science. It doesn't distinguish between them. So least squares, ordinary least squares, that's what it does. It does regression, or it's a logistic, any kind of regression. Or the arrow drawers, you know, the graphical guys. They mix everything up. It's always the observed value of something. So where's the insights? There's no missing data. So what do you estimate? Well, either I know the causal effects, or they must be parameters. Oops, they must be parameters. Something I have to make up, because I don't know what they are. But it became standard in biostatistics, economics, epidemiology, everywhere. And even great statisticians and epidemiologists, Fisher, Cochran, I'm not going to be, and a guy named Cornfield. Cornfield was the main guy in the tobacco and lung cancer stuff. Confuse themselves with the observed value notation. Do I have, what, 2 slides left? Yeah, 2 slides. So I'll probably get through them almost. But I won't go more than 2 minutes over, okay? So it's a bad influence on observational studies. There's no design phase. We got rid of the design phase. There's no design. Oh, we just take a data set and start analyzing it. Confused analyses, association versus causation, muddled. Actually, who was the first guy who used cause for a regression? And when was it? It was in 1898, I think. Yeah.
I don't know if he used the word cause.
He did. He did. He called the regression coefficient causal. A completely non-causal setting. He said these are like, what, birth rates or something causing crop yield or something.
He was interested in public policy and welfare.
Yeah, that's. He had 2 papers, I think.
A good idea to pay welfare without making people live in the poorhouse.
That I didn't know.
It's a very coherent paper. You would like it.
Actually, I did read it, but there's another one that was just purely math. And the math part was pretty good on partial regression coefficients and all that sort of stuff to find those things. So it's actually, you know, he's actually. But here's a sentence that's from Cornfield. I think is kind of meaningful. It's in the context of case control studies, which are really the meat 90% of medicine. A case is a person who has the disease. Control here is a person without the disease. So it's not like control in a randomized experiment. A control in a randomized experiment is one who gets the control treatment. So the use of control here is completely confused. But these case control studies, as they're called, are completely confounded because they're selecting people who are diseased, selecting on the outcome, and comparing them to people who are selected because they don't have the disease. Sure.
Can I infer from this that what you're saying is that regression and randomization were rivals or enemies or just didn't co-evolve the way they should?
They didn't co-evolve the way they should. That's right. But as being enemies, I don't think so. I don't think anybody sort of put them up against each other in a sense. Because the people who did randomized experiments were in this part of the world, and the people who did epidemiology and observational studies were over here. And they didn't talk. In fact, even now, I think, to find somebody who's in epidemiology or even biostatistics or policy or economics who's had one course in real experimental design, I think it's pretty rare. Albert, did you ever have a course in real experimental design talking about partially balanced incomplete block design? Teach it, yeah. But I think it really helps to have like a course where you actually learn all these different designs and how you can randomize and realize that that's how one way to define causal effect that's not tied to models. Here's this one quote from Jerry Kornfield in 1959. I think it's kind of revealing because he was a very smart guy. We now consider the distinction between the kinds of inferences that can be supported by observational studies, non-randomized, where they're prospective, match people who are smokers and non-smokers, or retrospective. Retrospective is case control. You match a disease with a non-disease. That can be whether prospective or retrospective, and the conclusions that can be supported by experimental studies, randomized experiments. That there is a distinction seems undeniable, but its exact nature is elusive. Well, is that really true? Elusive? There it is. In a randomized experiment, experimental design, it's unconfounded. You can't select a treatment based on your outcome. In an observational study, you're always worried about that. You're always worried about the people who got the active treatment got it for some unknown reason, and the people who got the control treatment got it for some other reason. Is that elusive? It's one line. You have to understand the notation, but it's one line. It's not elusive at all. Because they didn't use this potential outcomes notation. They used y-obs and put in regressors. So the starting conclusions, last slide, starting conclusions means at this point, retain key insights from the past, these Neyman and Fisher insights about randomization. Avoid confusion from the past, drop the confusion. And realize that, and also I think it's important to realize that these randomized control ideas are extremely recent. They don't go back to the Egyptians, they don't go back to the Greeks, they don't go back to John Stuart Mill. They're very recent. They're really 20th century ideas. Update statistical methods for both design and analysis. This is re-randomization for design and analysis, all the things that we can now compute to take advantage of modern computing environments. We've just scratched the surface of that. We're still using these methods that were great when that's all we could do, because we didn't have any computing. I remember, for example, there's a lecture that Cochrane gave, or maybe it was a week, I don't remember, on how you invert a 5x5 matrix by hand using the abbreviated Doolittle method. Well, that's what doing least squares is all about. And that's your only tool. Encourage mathematical precision, especially in notation and logical flow. Mathematical precision in deriving epsilons and deltas, who cares? But do encourage it in describing things in the logical flow. And precision can have critical consequences for challenging applications, for example, like distinguishing placebo effects from active treatment effects. And these can have important consequences for applications. Because when somebody is given a drug in a doctor's office, they not only get the active treatment effect, but they also get a placebo effect. So that suggests we're probably overdosing people, and overdosing can't be good for people. Thanks very much. I'm sorry to go 8 minutes over.